Welcome everyone to your experiment for pre-practical lecture. In this experiment, we will look at the symbiosis between an experimental photometric study and a quantum mechanical model. And our model of study will be for methyl red, which you should know as an indicator from your first year. So essentially what we want to measure is the pKa value of methyl red, for which we will use the acronym MRH, and for its deprotonated version we'll use MR minus. Of course, when the H is lost, it becomes an anion with a negative charge. And we will determine this pKa value from its absorption frequency, given the symbol nu, and of course nu and the wavelength at which it absorbs has a specific connotation or correlation, which you can easily calculate it from. We will do this using, we will determine this absorption frequency, so of course this nu value from the UV-vis spectroscopy, so that's our experimental way, which we will do this, and then we will, as an extension, calculate using the 1D particle in a box model, or in principle probably particle on a line model, to theoretically also calculate this absorption frequency, or well, the wavelength in essence. Okay, and the reason this works well is because methyl red is a commonly used indicator. So it's methyl red is red in the protonated form, so in its acidic form, and in its basic form it is deprotonated, and it's yellow, and when it's in these two different forms, it absorbs at two different wavelengths, in other words, two different absorption frequencies. So in the acidic form, it absorbs at 520 nanometers, and in the basic form at 425 nanometers. And that is why the experiment is actually possible, and we can use this information to calculate what we want to calculate and get the pKa. Okay. Of course, just to explain a little bit more, in terms of what you've seen in your prep guide, so we have the protonated version, and then we have the deprotonated version. So you see all the action is happening at this acidic proton over there in the MRH molecule, or the methyl red molecule, and at a certain pKh, there is this equilibrium, which has the switch over from the acidic form to the basic form, which is what we want to calculate. Okay, and of course, as I've already said, we have the two different wavelengths at which these two absorb, and you will determine on your day in the lab what these specific wavelengths are. Of course, these are approximate. It won't exactly be 520 and exactly 425 nanometers. You will determine that on the day for your experimental conditions. So specifically for this practical, you're going to make 1,000,000 solutions. But firstly, to start with, you're going to make the following 4. And technically, you first start with the first 2. So you need the first 2. If Joel was nice today in the lab, he would probably have made up both of these for you. But if you have to make them up yourself, I'm quite sure you will be able to do that. It says 100 cubic centimeters in the lab manual. It might be 250 cubic centimeters depending on, or well, 250 milliliters depending on what we have available in terms of glassware. Just keep that in mind. So do your calculations beforehand for 100 and 250 milliliters, just in case. Okay, so once you've made up number 1 and 2, you're going to use the standard solution in both the makeup of solution A and B, and you're also going to use the deprotonated or the solution of acetic acid or the acetyl solution in B, and another solution that will be provided to you in A. And a very happy coincidence is that solution A is the acidic solutions, and the solution B is, well, the parent solution of your basic solutions. So from here, if this hasn't made sense when you read the manual, what we're basically going to do now is we're going to dilute A and B to make a range of dilutions So a range of acidic dilutions and a range of basic solutions. And as I've sort of suggested already, please do the calculations of how much you need of each to do these certain steps, specifically the ones that are coming now, the dilutions, because these are written out for you. And if you have to move to 250 mils, it's just going to be multiplied by 2.5. But for the next one specifically. And of course, then please check with your demis beforehand. They will be able to assist you should you have made a mistake. Remember also, when you are making up these solutions, work analytically. So in other words, you need to use pipettes and volumetric flasks. You can't be using beakers and gung-ho cowboy ideas like you did in 385. This is the physical chemistry lab. Okay. So the next set of solutions you've made. So you sort of made 4 beginning solutions, which you're going to start with. That's what we covered in the previous slide. So now you're going to dilute solution A and B using 2 different. So this is an acidic solution diluter, if you want to put it as such. And B, you're going to dilute with a basic solution. Acidic solution, of course, contains MRH, and the basic solution contains the deprotonated version. So what the dilution does is you're going to take a certain volume of your solution A and add a certain Y volume. So X and Y are just variables, meaning some sorts of volume of your 0.01 molar HCl. And in total, it's going to be in a 50 milliliter volumetric flask. And you have to do that for 0.75 relative concentration, 0.5 and 0.25 relative concentrations. The reasons these are relative concentrations because it's not the exact concentration of MRH, it's the concentration of A in the 50 moles. So in other words, 100%, so 1. So these are fractions. So 100%, so 1.00 would have been completely 50 milliliters of A. So 0.75 is 37.5, 0.5 is 25 moles, 0.25 is 12.5 moles. In a 50 milliliter volumetric flask, and then you're going to fill up to the meniscus to the line with this solution. And you're going to take measurements at 520 nanometer because we are working in an acidic environment, so it should be MRH that is absorbing. The same with the basic. Again, you make up 50 milliliter solutions with the relative concentrations, and except now you're going to measure at 425 nanometers because we're working with the deprotonated version, the yellow version. So you are then finally, after you have all made up all those solutions, you're going to make 4 unknown solutions. So in other words, where we are not quite sure whether or not we have MRH or MR and in what ratio we have both of them. Because remember, in the previous ones, we sort of strongly dictated acidic or basic. Now you're going to make mixtures, and you're going to use some of the earlier standards you created, that 1 to 4 in the table on the previous slide, which you're going to use to make up these solutions. And then these 4 mixtures, or I'm going to call them mixtures from now on. So your 4 mixtures are you record their UV at both 425 and 520 nanometers. You will also measure the pH experimentally using what's it called, a pH electrode, which is going to basically just tell you what the pH is. It's very easy. You'll see in the lab. It's quite cool. Yeah. So the mixtures I was talking about are these 4 mixtures. So they explain to you how to make it up. So this total volume is 15 plus 25 plus 10 plus 50. So that's 60, that's 85, that's 90 plus 10 is 100. You see, so this is how you make them up. And then you're going to measure the pH and you're going to measure the absorbance of these. And then using some other things, we're going to calculate some other things. But that is the idea behind this table in table 4.1 in your practical guide, so that you can make your experimental notes on it of its absorbance. Remember, you also need to take the absorbance of the other mixtures you have. Okay, so just a nice way of visually summarizing what we've gone through. So you start with these 4 initial solutions. So you have the acetic acid solution, you have the standard solution of methyl red, you have solution A and B. Depending on what you're going to use, 250 mils or 100 mils flasks, that will be determined on the day. Like I said, prepare for both. So prepare all these as if you're going to make them in 250 and make 100 mils as well. Okay. Then solution A and B are going to be split in 50 milliliter flasks, meaning that 0.75 relative concentration, the 0.5 and 0.25 for each of them. And remember how much volume it means. You need to take from A in this flask and need to fill up with the HCl solution, and in this one fill up with the acetic acid solution. And then finally we have our 4 unknown mixtures, which we have here, which will be in 100 milliliter flask, because we know that will be 100 milliliters we make up on the day, and you're only going to need 100 mils for them. So they sort of removed from the other ones. You do use this solution and the standard solution in the makeup of these as well as another acetic acid solution, which Joel should provide you with. And these are done in 100 ml flasks. Okay, and get ready for it. This is the coolest picture you'll ever see in your life. You should end up with something that looks like this, a bunch of beautiful solutions, all different, well, not different colors, or different colors of red and yellow. This is actually a picture from my 3rd year when I did this practical. It should make for some beautiful work, which I hope gets you excited to do this practical for yourself. So you will start with taking absorbance measurements for the dilutions of both the solutions A and B. So you will have 4 solutions plus a blank, so that's a 5th measurement in principle. So in other words, a 100%, which is solution A and B, and then their dilutions of 0.75, 0.5, 0.25, and then the blank, which is in principle 0, or 0% relative concentration. And then from that, you will measure their absorbance. So for the acidic solutions, you measure the absorbance at 520 nanometers, and for the basic solutions, you measure the absorbance at 425 nanometers. In other words, then you will be able to construct a correlation or a linear line of regression of absorbance versus the relative concentration. So in other words, if you know what the absorbance is, you can correlate that to a relative concentration. In other words, you have the concentration, the relative concentration, you're going to have an absorbance measurement, and in Excel, you're going to have a line of best fit plot, which you're going to do for both of them. And of course, that then gives us the line of best fit, which we can use to get a relationship between the concentrations of MRH at specific wavelength and MR minus at its specific wavelength to relate the concentrations. So let's say, for example, we're looking at 520 at an unknown solution. We get a response of a certain absorbance, and we can plug it into this equation, and we can know what the concentration of MRH is, or the relative concentration of MRH is. And we know, we scan that same unknown solution at 425 nanometer, then we know, and we plug it into this line of best fit equation, then we can calculate the relative concentration of MR minus. Right, so that's where we're working towards. So these are what we call calibration graphs. So that's why I say it's the basic and acidic calibration graphs. So we know how to relate absorbance to relative concentration. Then moving on, once you have these calibration graphs, and of course they're linear fits, you're going to take your 4 unknown solutions, or your 4 mixtures, and you're going to measure their pH and their absorbance at 520 and their absorbance at 425. You're going to tabulate that, and for the next one you're going to do it, the 3rd one and the 4th one. You're going to do it. You don't have to do it in that sequence. You can do pH and then all the absorbance in one go. And then from that you use your values. Remember, we had A equals AX plus C and A equals BX plus D. So this one, it goes with at 520, and this one goes at 425. So you plug it in, you solve for X, because these A and C and B and D's would have been determined by your lines of best fit. Solve for X, and that gives you the concentration of your methyl red species or your deprotonated methyl red species. So then for our 4 unknown mixtures, for each of them, we have a concentration of MRH, we have a concentration of MR-, and we have a pH. And if we take ourselves back to first year, glorious first year, when we had our youth and whatnot, then we remember if we were given the concentration of something in its basic form and the concentration of its acidic form, and we were given the pH, we could use the Henderson-Hasselbalch equation to calculate the pKa for that solution. In other words, we have 4 mixtures and we can calculate 4 pKa values, or technically pKa prime values. Remember, you can read the practical guide on exactly why I use the prime notation versus just the normal pKa notation, the activities and whatnot. And then you get 4 different, they will be slightly different, they shouldn't be completely different from one another, 4 pKa values, and then you will average those pKa values for those 4 solutions. And that average value you can compare to a literature value for methyl red. So you can look up the methyl red literature value or the pKa value for methyl red in literature. You need to reference that, of course, using the RSC referencing style. I hope you still use that. Well, you definitely should be using it by now. And of course, you can discuss any discrepancies that you see, reasons you might think of, etc., in your discussion section and whatnot. Okay, so that was the experimental side of the experiment. And now, let's say, for example, we did not know our methyl red is going to absorb at 520 nanometers and our deprotonated version is going to absorb at 425 nanometers. How would you have gone about it to determine what those wavelengths were of absorption? Now, one way is, of course, look it up in literature, but another way, in a way that we can use quantum mechanics, is that we can calculate what that absorption frequency should be. And specifically, since absorption or UV-vis has to do with valence electrons being excited to a next higher state, the perfect example here is a particle in a box model, but specifically a 1D particle in a box. And because we have a conjugated system, this electron can technically move around this whole molecule, not there, but through everywhere where it's conjugated, the electron can move around. So if we approximate this molecule as a one-dimensional box, meaning the electron basically can move on a line, that line has to have some length, box has to have some length, right, of L. And unfortunately, we need this L before we can do any calculations using the quantum mechanics, because we need to know the length of the box the electron is restricted in. Okay, but how do we calculate L? So let me just change here to the highlighter, and let's take the red one. So what you're going to do is you're going to start here, move through the molecule, move through these bonds, move there, and finish there. Okay, so that is where you start and you finish. So then Practical Guide gives you a summary of sp2 and sp2 oxygens and sp2 carbon, sp2 carbon, sp2 carbon, sp2 carbon, sp2 nitrogen, sp2 nitrogen, bond lengths. So you can go determine with 1, 2, 3, 4, 5, 6, 7, 8, 9 bond lengths and sum them up together and get to L. Okay, you can check with your demonstrator that you've correctly used the correct length for your box. Okay, so that is how we're going to get L. And like I said, it's listed in your prac manual how to determine what the lengths are that you may take for these bond lengths. So this is the path the electron will be able to move during its excitation or subsequent decitation. So once we have L, we can use our quantum mechanical model for 1D particle in a box to calculate the energy of a specific energy level using this equation. So n squared h squared over 8ml squared. And we can also use that to calculate the subsequent transitional or energy required for a transition from one energy level to another. In other words, how much energy is required to excite an electron from one energy level in the particle in a box to the next level. In other words, exactly what the UV-Vis data implies. In other words, you can then relate this energy value to a frequency or a wavelength value, which is ultimately what we want to get at. Right, just a few things to go over. Remember, h is Planck's constant. The m in this equation is the mass of the electron, which you can look up. L is, of course, as we calculated before, for the particle or the molecule, and n is the quantum number, which runs from 1 to up to infinity. And if you plot the energy levels using Excel, it should look something like this. You should get a nice, it should have an increased spacing for each increasing energy level. Makes sense from this equation. So it is proportional to n squared. So in other words, the spacing should increase with each subsequent energy level. And you can do it quite nicely with Excel. I would discourage you to do it by hand because you will mess up your spacing. And you should quite easily be able to do it with Excel with some clever thinking of how to do it. I did this, of course, in Excel, and I'm an idiot, so I think you should quite easily be able to do it. Yeah, so once you have this, of course, then we can start discussing how do we then decide which energy transition is the one that correlates with the one we see in the UV-Vis spectral. In other words, which is the HOMO-LUMO transition. In other words, which is the highest occupied molecular orbital, which is the highest occupied energy level, let me rather use that term, and then in other words, to which energy level does our electron jump, essentially, or does it fall back down to for it to release the photon. And that can be correlated to a wavelength or a frequency value. What are we going to do with that? So we want to calculate the absorption frequency, right? So in terms of absorption frequency, we're looking at an electron transition from its highest occupied state to an excited state. So what is the energy required to make that movement, right? And it says in the Prac manual that MRH is a 10 electron system and MR minus is a 12 electron system, which we can use by filling our particle in a box system. So if we take our energy levels and we put in 10 electrons, so 2 electrons in the first energy level, 2 electrons in the second one, 2 electrons in the third, the fourth, the fifth. Okay, anyway, I hope you all just heard the joke that was playing in my head. If you've ever watched Shrek, you'll know what I'm talking about. So yeah, okay, good. Sorry. Then you see the highest occupied level here is n equal to 5. So n equal to 5, so meaning the transition for this molecule, so if we take some wavelength coming in, it's going to excite an electron from the 5th to the 6th energy level. So that then means that our delta E is the 6th minus the 5th energy level. And that we can correlate to the frequency of the energy required, or the energy radiation required to make this excitation. In the same manner, we can do it for MR minus, except now we have 12 electrons. So we can go 1, 2, 3, 4, 5, 6. So its highest is the 6th level, and its excitation will be then to the 7th energy level. So meaning the difference in energy, delta E, is E7 minus E6. And these you can calculate from the equation from the previous slide. And then you get delta E, and it should, then delta E may be used to calculate nu, which is the vibrational frequency of our electron. Okay, so now we have vibrational frequency, and then it's a simple task of relating vibration frequency to wavelength, and you can see that it's C, what is it? It is lambda over C, I can't remember. Which you need to look up, just look it up. How to convert frequency to wavelength. It's in the Prac manual. And then you have what the absorption frequencies were predicted as per the particle in the box model, and you also have them as you use them in the experiment itself. Okay, so finally, compare these calculated frequencies just to the absorption frequencies we use, 520 and 425. As I said, might differ slightly on the day that you do it, but then compare those and evaluate how well the model predicts these values. In other words, does the model predict them well? Should we perhaps, what should we change to the model to better our answers or better our estimates if we were completely out? Let's say we get 700 and this needs to be 425. What kind of assumptions did we make to break down certain things? Did we, for example, model a flat planar molecule which is clearly a 2D species as a 1D species? I wonder. Those kinds of things that you need to look at. Also, maybe the complexity of the model. Maybe a particle in the box is not the correct way to model it. Maybe there's a better way to model it. Should we perhaps have used harmonic oscillator mechanics? I don't know. Try to see if you can think of something else, and then, like I said, to evaluate how well the model predicted these values. Okay, I hope you're going to enjoy this practical. It is a bit long. It's probably the not one of the longest, but it's one of the longer practicals. But it's a lot of fun, like you saw. We can take nice pictures. I'll be in the lab. Your demis will be in the lab. Please ask us a lot of questions in those times when you're just waiting around for life to happen. And yeah, I hope you enjoy it. I'll see you then in the lab.